Ladies and gentlemen, welcome to another video on this channel. My name is Jan, and today we're going to talk about 3D printers again. As you may or may not remember, a few years ago I built this 3D printer out of a Johansson CMM. It's all made of granite, weighs 1.3 tons. For the first step I just converted it to a regular Cartesian 3D printer. And then the second step, I added a conveyor belt to eject parts. There's somewhere a like 7-part series on this YouTube channel. Not long ago, I had a few sleepless nights, and yeah, there is a second one of these CMMs here. I couldn't stop thinking about what to do with it. It's this time of the year where I have to build a 3D printer. I guess that's how I am. And yeah, I settled on a plan. And that is to eventually build the fastest FDM printer out there. In terms of how to measure that, there is the Speedboat Challenge, which is kind of the benchmark for quite some time. I think the community has done a really great job at doing that, and it's also helped a lot of commercial machines, like, for example, these guys, and also the Prusa machines, of course, to like see the demand for fast printing, and the guys in the Speedboat Challenge really helped to develop that. So without further ado, the second CMM is kind of in a state that looks like this. If you have no idea what's going on here, well, I think I have to explain a few things. Let me get a break here, let's play the intro, and we'll get into all the nitty-gritty details.
Da 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 da.
For going crazy fast in FDM 3D printing, I think we have to solve 3 main issues. First of all is how to build a really fast motion system. That's obviously needed. The second thing is that all the other guys participating in the Speedboat Challenge are complaining about their hot ends not being able to keep up with the flow rate. So that's a huge thing we gotta address. And with extruding more and more plastic, you need to cool it somehow. And that's the third thing we have to work with. To solve this issue of cooling, this machine will run on shop air. Let me specify, loads of shop air. So this is a distribution system, and as you can see, all the stepper motors are actively cooled by shop air, as well as the electronics of the main board. The cold end will be cooled by air, and also part cooling will be done by air. And yeah, we'll see if that works or not. As of right now, I think we're gonna go with a no fan solution and see if that works. I mean, this printer will not run for 24/7 or something like that. That would be a huge waste of shop air. It's a very expensive media. But I think for the actual uptime of this machine, this is a very sufficient solution, and the cooling capabilities of shop air are really high. So let's see how that works, and you will see at the end where all these connectors go to. Next step, I want to address what to expect in this video. So we talked about issue number 3. Next video will be about building the hot end. And I don't want to make any promises, but if I get the time to edit this video today, I will be posting it next weekend and have, like, just foreshadowing, I'm planning to build a hot end which will be able to extrude somewhere in the neighborhood of 250 to 300 cubic millimeters a second, which is a huge number. And I have no idea if that works or not, but yeah, the plans are done. I have a plan how to machine it, so let's see how that works out. And for the rest of today's video, I'm going to explain a few things about issue number 1, the motion system, and I think we can build the Z-axis together. I have the parts just finished on the 3D printer. Yeah, we can hook that up too and have like the motion system explained to you guys. So let's have a look. The motion system is centered around, maybe to give you guys an analogy, building a drag car, which is only designed to go a quarter mile in the fastest time, and there are no compromises in doing that. There's no AC, there's no radio whatsoever, and I think this is a pretty good explanation to what's going on here. I got rid of everything you don't need. We're building a bed slinger here. This is the bed that is actually going to move. We're not gonna print on a heated bed or something. This golden thing in the middle is actually what we're going to print on. Most of the other guys and girls started with an existing printer like an Ender 3 or Voron series. I thought that is going to give me so many compromises from the start on, because I have to work in an existing system. I tried to just build it from the ground up. When I tried to compare it to existing like Voron systems or something, those guys have, compared to my system, a rather big mass to accelerate. I got a few numbers when you include like rails and extruders and fans and belts and whatnot. You are somewhere in the neighborhood of 200 grams you have to accelerate. And I wanted to get that lumber as low as possible, and also create the least amount of friction on it. This setup as of right now is about 53 grams of total mass to be accelerated, and I got plans here to go somewhere in the neighborhood of 30 grams. We'll see how that works out, but I'm not gonna go into too much detailed work until I get the big picture stuff going. As I said, with friction, all the other guys use V-rails or linear guides or whatever. This thing is actually an air bearing as of right now. So the thing is, with this CMM, it's powered by 18 air bearings. We're not going to use that motion system, but I've built an air bearing by myself. So this is a pretty thick granite table. And what I did is I drilled a hole straight through it and epoxied an air hose on there. So that way it can flow air supply from underneath. And I got an earlier version of the moving table, whatever you want to call it, here. And what actually happens is this dome, air is coming in here, and there are channels to distribute it to the outside patches. And then there is an outlet on the bottom and on top. This is actually gonna let it float like an air bearing. On top there will be, this is just a prototype I have on here, there will be this made out of glass. Space in here will be very precisely lapped to the height of this part. What will end up happening, and I'm going to insert a video here where I made the initial tests about it, this will be pretty stuck at the start and won't move at all. And once air is applied from underneath, actually move the system frictionless. To address the elephant in the room, this isn't a Cartesian 3D printer. It's actually derived from the Clipper built-in winch setup. So basically you got these systems that are, you have an actuator somewhere hanging in the middle from 4 ropes, or 3 or 16 or whatever. The Clipper is determining the length of each rope in terms of the actual position of the actuator in the room, and it does the Z-axis movement by lengthening all the cables at once. that it is hanging down. In this system it's actually quite similar, but I had to get rid of the Z component because I don't have that lengthening of the cables in here. It's just the XY. Movement of the Z-axis is transferred to a different stepper, which is sitting up here. This is just in the XY plane moving, and there will be a Z-axis that is lifting up the extruder. And that way we can have all of that down here as light as possible, and we don't have to make any compromises in terms of what the extruder will be up there. We don't have to watch out for weight. The motors itself are LDO Speedy Powers, and they got a pulley on there, which is quite interesting. So basically there is a very high strength rope, Dyneema type, which has very low expansion when forces are applied, and this is being fed through two eyelets. On the backside there is a spring to counteract like the forces of the rope tension, and it gets like pushed on the another track. I just hit my head like for the 100th time, but it gets fed through these different eyelets. The whole motion range of this system is exactly as big as you need for 3D printing a Benchy. This is like 30 millimeters in each direction. And that is exactly how I designed this pulley to be. It's 25 mil in diameter. So basically with the 3/4 of a rotation I can do, it's just enough to feed the wire 30 millimeters in each direction. As you can see, when this is in the middle, also this loop is in the middle. And we can, as you can see, this is basically all it has to do. Very interesting thing about this setup, if I pull this wire, have a look what these guys are actually doing. So as you can see, for every move, all the 4 motors have to interpolate their motion. That's why we can have a very high power density of all these motors on a very light part in the middle. We're going to go very briefly on the electronics and supply, etc. And I want to give you guys an example of how this is working and moving to not get you starved on information. So we're using everything, I guess, is state of the art for 2024. This is a Raspberry Pi, a big TreeTech Octopus. I have 8 motors running when everything is hooked up. As I said, motors are LDO Speedy Powers, and under this cooling supply you can see they are TMC 5160T Pro stepper drivers, which are like state of the art, and they're driven by a 60 volt supply. The mainboard itself is powered by a 24 volt supply, and yeah, that's pretty much it in terms of electronics. All of that is connected to a Clipper software. I'm running Mainsail as of right now. A quick heads up at this point for 2 things before we get any movements done. In terms of setting this up and programming the firmware, I had some help by Julian, which is also the guy that helped building the solar robot. I'm pretty sure he will pop up in future videos about this topic. And also, this is very important at that point, I think the whole thing here with fast 3D printing is a thing of a community. So I'm posting this video as of right now because I want to make it as open source as possible. Eventually, you don't need a big ass CMM. This can also be done on a wooden board or something. You don't need the shop air part, it will run without, and you can go really fast with the setup itself and also with just some basic motors, not the expensive ones. So I want to give all of you guys the opportunity to build that by yourself, and I guess maybe I will do a GitHub or something later on, But as of right now, we're gonna post all these information on the Discord server that is below. And also, last time I talked about the Discord server, I mispronounced something, which was not my intention. I set this up in the first place when I was talking about the robot, I guess, but I had huge help from a guy named Jordi, which has been a great administrator of the server. He did all the setting up of all the settings, etc. I have no idea how to do that. If you guys want to join the server, there will be a link down below, and you can find, I guess, information about this machine. I have just a general discussion, and follow that with more information than you can see on these videos on YouTube. I think I have let you guys waited long enough, so just let's see how this machine moves. So alright, everything is hooked up. We're gonna go with printing a 3DBenchy. I mean, it's just a dry run, obviously, but this is expected to be 6 minutes and 8. Obviously we can go a lot faster, but just for demonstration's sake, I already uploaded this, and I have the speed factor limited to 10%, and we're running 50k accelerations and 50 square corner velocity. So I'm just gonna go with print. So this is hitting speeds up to 120 millimeters a second. All the noises you hear is because there's actually shop air coming from below, but there's no counter pressure. So if I put my fingers on here, it will get significantly more quiet. Alright, so let's go here and just put in 50%. So now we're reaching like 600 millimeters a second. It's looking like this. And now let's go for 100%. I guess it's gonna make it. I have the motors tuned down quite a bit. So yeah, it's getting up to speeds of like 1,000 millimeters a second. I think 1200 is the max. Yeah, let me wait out the compressor. Alright, so this time we're gonna like continue the print, and with the steppers turned down to 1.5 amps, I may think we're gonna go with a 100k acceleration. And when I hit stop, so apparently steppers didn't lose steps, so it made it. But we can have a full go at it with all the acceleration I got as of right now, but I have to like get the motor current up again. So let me do that. Alright, I'm back. Made a few changes. As you can see, I removed the print bed because this was part of why it was tipping so much, and so now it's a lot more quiet and I guess more enjoyable to watch. So this time we're just printing a 2-layer circle, which is 60 millimeters in diameter, so it's basically covering 95% of my printing area. I already uploaded that. The max speed is set to 800 millimeters a second, and the acceleration is at 200k as of right now. Let me switch on this and hit go. Alright, I'm going to plug in 250k acceleration, and we're just going to go again. And we're going to do the same again with 300k acceleration. Oh, wait, that was 3 million. And here we go. So I guess one of the drivers overheated, because I'm not cooling that as of right now. Yeah, they get in pretty toasty. So most of the time they do shut down somewhere in the neighborhood of 60 degrees. Yeah, they are quite warm, as well as the motors. So with these settings, I'm running these at 3 amps, 2 minutes of going at that speed, and then everything is basically boiling, the motors as well as the motor drivers. But long story short, when I hook these up to actually cool, it's pretty loud in here, and for filming purposes I don't want to do that. So I can tell you from previous testings that with this setup and printing just a circle, I can like reach 350k accelerations. It goes down a bit when I'm actually printing a real object like a Benchy. May be able to reach 300k. But there are many things I consider to up these numbers for the future. So there is no input shaping. There is one hell of a lot of parameters to find. I mean, there is spring rate, there is pulley diameter, there's different motors, there is the length of these cables here, micro stepping. Maybe have a look at the cycle times of that Raspberry Pi. I don't know what the bottleneck as of right now is, and it's gonna be my, and maybe I hope our job to find all those perfect parameters. So my ultimate goal would be to have that system run somewhere around 500k accelerations, but I think there is one hell of a lot of work to do, because what I can tell from previous experiments, if I run these motors in this setup with the state-of-the-art drivers, etc., without any pulley, just free air, they step out at around 450k accelerations. I'm kind of in a debate with myself why that is and where the bottleneck is, and if some of you made your own experiments with this, I'm really happy to know in the comments why. I mean, what you can improve on the base in terms of programming, the Pi, does it have enough computing power? If you guys are running stepper motors without any load attached at around 1 million K acceleration, let me hear what you do differently. That would be highly appreciated, and then we can apply it to the system with just the bare minimum of mass to be accelerated. I just had a look at that footage from what my camera is picking up, and I don't know if that's after rendering looks the same. It honestly doesn't look too impressive, but let me tell you, if you see it in first person, you already start to really, the object that's moving is quite kind of disappearing to your eyes. So the camera isn't picking that up any good. If you're wondering why we're running 800mm stops, so as I found out with all the other guys doing speed benchies, that's kind of the sweet spot with the current versions of hot ends they're running. Basically, it's not possible to extrude any more plastic. I actually ran these up to 3 meters a second, but as it turns out, I have to go quite low with the deceleration in that, and it turns out it's faster to go maximum acceleration and just follow up with a decent amount of speed. With this setup, I was able to dry run a benchy of around 3 minutes 20. So there's still loads and loads of improvement to be done to go near some kind of a world record figure. But as you can see, there's not even extruder on here. So I think as a proof of concept, this works out. And I'm sure that I would, when I just like follow Albert's instruction on the Voron series, it would be way easier to go down like 2 minute 30 or something. I mean, it's a very hard thing. I have absolute respect for all the guys that are doing this and fine-tuning all the parameters, etc. But yeah, I'm gonna go with this approach because it's something different, and yeah, it may push the technology even further, and that's my approach, like with all the other things. So I guess because dry running is pretty boring, we're gonna go ahead, set up a camera, time-lapse the z-axis. I got 2 bearings missing, so we can like hook this up, but I don't know if it will move. The other bearings are in the mail. And yeah, next week I'm gonna focus on the extruder, building that, and maybe at the end of next week we're gonna have some very basic, first print of this machine. We'll see, but I won't promise anything on that, but I hope that I can achieve my personal goals. I'm also not saying that I will be faster than anyone else. As I said, I have huge respect for the whole community doing this. We'll see what the end result is, and I would be really happy to break some records, but yeah, I don't know how much time I can spend on this project. Like with all the other projects, you start it and think, okay, I can do that in a decent amount of hours, and I'm already tenfold in that, so we'll see. We'll see, but I have you guys on board. This is what I came up with yesterday. This post is really, really solid. If we stick an indicator down here and apply greater forces, it will actually just move by microns, maybe microns. This setup has to be called rigid enough. And because I don't want the z-axis to be the bottleneck of the whole mechanical system, I didn't want to have this huge mass accelerated. I did that with that machine. There is a servo motor and a ball screw which moves that, and for this kind of big behemoth that works quite well. But for this machine I want to go with something very dynamic, and that's why I opted to have this in kind of the right position and just put another z-axis on top. What I did was just use this post as a mounting feature. These just hold these grounded rods, and on top of that I have some ball bearings running. As I said, the right one is bad. This one is Misumi one, and I ordered additional 3 for completing the setup, but it works for as of right now. And here I got just a NEMA 17 stepper with a 20 tooth pulley, which is driving a GT2 belt. And yeah, this is like the counterpart, and it's just clamped here with a tooth profile. I haven't looked at the maximum possible speeds, I just typed in some values. Also, it's running off the 20 volt supply right now instead of the 60, and we're running 500 millimeters a second with 25k acceleration. I think that won't make it a bottleneck. And if I hit go on my script, so yeah, that's 73 millimeters of travel. I think for the Benchy I need somewhere like 52 or something. But I wanted to give me some headroom because maybe my hot end will be a bit larger. Yeah, so I do have some kind of a wiggle room. To give you some kind of an outlook, all these mounting holes will be needed to have the hot end sit on here. I don't want to give too much away for right now, but I guess it's safe to say this will be rather special hot end. I mean, a standard E3D V6 wouldn't fit here, right? And yeah, for the last step of today, I'm just gonna like dry print this cylinder. It's 15 by 15 by 15. Printing that with the Z-axis installed looks something like this. I got the speed set to 50%. I mean, it's way down. It's like 50k accelerations just for purpose of having a look at the Z-axis. Alright, that works out. I guess that's it for today. I'm gonna head over to like my parcel shop to pick up the bearings and yeah, get the Z-axis completed. The hot end is actually the next thing I'm gonna tackle, and I don't know how much I want to give away from that as of right now, but I guess all of these components will go in here and quite a few more. There will be an industrial heating situation, there will be loads of brass, aluminum, and loads of machining. I'm gonna do that all by myself, so I would really appreciate if you guys hang out with me. As I said, there will be a link for the Discord server down below. I have no idea how much infrastructure in terms of that is going to be there once this video is going live, but let's see. I mean, this is a community project after all. I want to give all my information away. And yeah, I'm quite aware that I was just talking about a project that I've been very involved in for the last couple of weeks, maybe month, with on and off relationship. Post all the questions you got down in the comments and I will try to answer them in the next video. So, bye bye.